Hey there, we're here doing some physics, not playing Star Wars. And what we're looking at here is an inelastic collision as a practice problem. This is practice problem A2 for inelastic collisions, so collisions where momentum is conserved, but energy is not. And that's because we are deforming an object in some way. Either we're boring into it or it's being ripped apart. Energy's lost somewhere, okay? Even if it's just sound, like energy's lost. So what we have here in this problem is a 10.5 kilogram block. So here's a nice picture that we already have here. So this block is 10.5 kilograms. And it's sitting at the end of a horizontal table, and it's attached to a spring, and this table is frictionless. So that's nice. We don't have to worry about friction. The spring is just at rest here. And we fire this projectile like a little bullet, which has a mass of 0.05 kilograms. And this bullet is moving at some initial speed, which is 85.5 meters per second. Now the bullet bores into the block, but then it gets stuck. So we know this is an inelastic collision because it's, deforming this block, but momentum is still going to be conserved here. And we happen to know the spring constant of the spring is 105. What we're looking for is how many meters does the spring compress? Because we could have to imagine that as this bullet hits the block, it goes into it, but then once it gets stuck, it's that spring is gonna just get compressed to the right by some amount. Maybe a little, maybe a lot. We don't know. That's what we're trying to find out. So the way we solve problems like this are we always will conserve momentum. Energy isn't conserved, but momentum definitely is. And if recall from Unit 7, whenever we conserve momentum, that's initial momentum is equal to final, and each momentum is a mass times a velocity. So for our first object, which is like the bullet, the projectile, it has a mass of 0.05 kilograms naturally, and it has a velocity of 85.5 meters per second. The initial momentum of the block is 0 because it's not moving. So then we look at the final. Well, on the final side of this, the bullet and block are stuck together. This is a completely inelastic collision because they've been stuck. So the masses are going to be combined. It's going to be 10.55 kilograms. And then this block bullet system now, the combination of the two of them, it's going to have some final velocity. But we don't know what it is because that bullet's been lodged in there and we need to figure it out. Okay, but it's going to have some final velocity once that bullet enters in. Now, on the flip side of things, we can also conserve, or we're rather not conserving energy, but we can still write an energy equation. Now, this velocity here, which we'll call whatever we want, we call it the velocity of the target, I guess. That's what we did for the ballistic pendulum, at least. That velocity of the target is now going to actually compress the spring to the right. And if we do this, we're going to see that the block bullet system is going to have some kinetic energy here. Its kinetic energy would be 1/2 times the mass of the block bullet, so 10.55, multiplied by this VT squared. And we don't know what that VT is, so it's just going to stay like that. Now, this energy after this collision will be conserved here. So to compress this, well, it's on a flat table, so there's no change in gravitational potential energy. And because this block is eventually going to stop, there's no kinetic at the end. There's just the compression of the spring. So there's some spring or elastic potential energy, which is a 1/2 kx squared. Our k, our spring constant, is 105 here. And then we get x squared. This x is what we are looking for. So what we're going to have to do here is solve for VT, plug it down below, and then solve for x. Pretty straightforward, just a matter of running the math. If we solve for VT up here, we're going to do this just by dividing by the 10.55 on each side. And when we multiply and then divide, we find that VT is going to equal 0.405 meters per second. 0.4 if you're rounding, doesn't really matter. We're going to bring that down here. Now, if we were to write this out, we'd have something like 1/2 times 10.55 times 0.405 squared equals 1/2 times 105 x squared. Neat thing about this is the 1/2s are actually going to divide out, which is nice, which means that the only thing we really need to do to solve for x is divide by 105 and then eventually take a square root. So what this will look like a little bit cleaner is it's going to be the square root of 10.55 multiplied by 0.405 squared divided by 105. And yes, we could just square root the 10.55 and the 105 and then get rid of the square on the 0.405, whatever. But this is just what it will be without simplifying it or working that down. Sometimes it's easier to leave it like this and just let the calculator do the work. But that will equal the compression distance of our spring. And we throw that all through the calculator, we will get a quantity of approximately, given some rounding, of 0.129 meters. So just like that, another inelastic collision has been solved. We are still conserving momentum and then using that idea to plug back into energy, which was not conserved, so we can solve this problem out. So with that, this is finished. Until next time, adios, and take it easy.